Hello, and it is, yes, the last talk on Friday afternoon, and everyone keeps apologizing for graphs, and I am not going to apologize. These are fabulous graphs. They're lots of fun. We're going to have a good time looking at some harmonic analysis of the currents within Humboldt Bay. This is some work that I'm doing with my awesome undergraduate students in physics and oceanography. I've got three of them here in the back right there. Taylor Chukau, Caitlin Williams, and Steve Gracie are here with me, and there's also been other undergrads who've contributed to this, including Noe Camarillo, Emma Modrick, who's currently at University of Washington, Izzy Marcus, who is now at the U.S. National Ice Center, and Karina Bernbeck, Simon Kurskiski, and Max Sereno. So the overview is, why do we care? So motivation for looking at currents in Humboldt Bay. Why are these important? I don't know that I need to motivate any of you. I think you all think that the currents in Humboldt Bay are very important, but I'll give you a couple reasons. So one thing that we'll look at are a previous project where we looked at some of the controls on microplastics in the bay with another set of undergraduate students. And that is one of the motivating ideas for why we're looking at the currents now. Another set of undergraduate students, we looked at the controls on pH in the bay. And that also was leading to why we want to look at the currents now. Then we're going to look at some current velocity spectra. Again, very exciting, fun graphs for Friday afternoon. And then we'll be able to pick out from those tidal velocity spectra, we'll be able to pick out some of the tidal components and actually see what the different tidal components are that we're seeing in the data. All right, so some of the controls on microplastics in Humboldt Bay. To start, we wanted to see what those controls might be. And one idea was that it might be coming from tidal influx from coastal waters. And another was looking at tidal mixing. And so actually mixing up of the microplastics that are in the sediments. And so first, to get started, of course, you've seen Humboldt Bay. We all know this. It has a very large tidal prism, about 44% in the North Bay and 66% in South Bay. And this area right here of Humboldt Bay, if we blow this up right here, looking at some of the data from, if we look at some of the data from right here around where we have this marker here for MB4, if we look at that tidal data and some of the tidal data at other locations, we were able to draw these tidal lines. So these are co-tidal lines. They're 5-minute co-tidal lines that were drawn by Izzy Marcus for this paper on microplastics. And we can see how that tide is propagating in the bay, looking at those co-tidal lines. So what the idea was to use this propagation of the tide and to see how that might affect the microplastics in the bay. And so the sampling was done at different points in the tidal cycle, intentionally looking at the flood as well as the ebb and also during slack tide. And what the students were able to see by taking these different sampling stations and these different sampling tides throughout the tidal cycle was that at different points, either during slack tide when we had less velocity. So this is the velocity here. So we have velocity and it's velocity squared. What we're interested here in is just seeing how fast it's going and how much energy it has. So the velocity squared, we are calling that that's the velocity covariance, but it's really just like how much energy do these particles have? So how much energy does the current have? And we can see that energy is increasing this way. And as the energy is increasing, we see that the microplastic concentration, for the most part, at nearly every station was also increasing. And so that gave credence to this hypothesis that potentially we've got this tidal mixing that's stirring up some of the microplastics in the bay. There were some stations where it actually was decreasing. The station right here, we saw a decrease, and that is a station that was right next to the marina. And so we had a lot of boat traffic at that point. And so that was the reason that we believe that actually had a decrease at that point, was because it wasn't just being controlled by the tides. So that first idea is why we care about the tidal mixing in the bay, is because we see that it can impact some of the stirring, bringing up some of the sediment and potentially giving us more microplastics in the bay. All right. So we saw that when we had higher covariance, so that's basically more energy, we saw higher microplastic concentration. And so that's telling us that the tidal mixing is actually stirring up those microplastics in the bay. So the next project that is kind of another motivating factor for why we're looking at these currents was looking at the controls on pH in Humboldt Bay. And again, one of the hypotheses was to look at potentially tidal influx from coastal waters. Potentially we're bringing in different pH from coastal waters, as well as looking at, again, this idea of this tidal mixing. We have this big, huge tidal flux in the bay, and perhaps we're getting some carbonate sediment that's getting stirred up with the tide and leading to some carbonate sediment dissolution that would then be able to act as a buffer for the pH. The next idea to look at was, of course, biological productivity and respiration. So we've got lots of biology going on, including eelgrass. We're talking about lots of eelgrass. And also we have all the shellfish, right? So we've got shellfish, that's another biological, both a producer in the sense that it's taking up some of that carbon and making the shells, and also respiring. So those are some of the potential controls on the pH in Humboldt Bay. And so to look at that, the first thing I want to point out is this graph here. Is very cool, fun graph for a Friday afternoon. We're looking in the top in A, this is showing, the top is in Humboldt Bay, and we wanted to have a comparison. So the comparison here is at Trinidad. And so we have Humboldt Bay in part A, in the top graph in A, and then Trinidad in B. And what we can see very clearly as we look at the pH, which is blue, and comparing that to the water depth, which is basically giving us a tidal signal, we see a very clear tidal signal that's controlling, which we expect. We expect to see that very clear tide as that depth is alternating. And we can see that the pH is in fact, when the tide is low, we're getting a higher pH. And then when the tide goes up, we're getting a lower pH. And so we're seeing a very clear pattern that the pH is actually being controlled by this tidal influx in Humboldt Bay. And as a comparison, we wanted to look at what was going on at Trinidad. And so at Trinidad, we see that, in fact, we still see, of course, a strong tidal signal. We would expect to see a strong tidal signal, but we don't see that same pattern in the pH. So the pH was not being controlled by the tides in Trinidad Bay as it is in Humboldt Bay, which leads to the support for the hypothesis that we in fact are having pH waters that are being brought in from the coastal waters that's actually controlling, for the most part, the pH in the bay. Here's another diagram, very similar, but this one we see a very longer period, a longer time period. And so we can see early on, right here, where we have that same signal. So we have the pH being opposite to the tidal flux. And so when there's a low tide, there is a high pH and vice versa. However, we see that there are moments where that starts to shift. And so in this longer time period, which is the first 19 days of July, we see a shift. And then this shift is showing us that while we usually will see that the tide is bringing in a higher pH water, there are moments where that actually shifts. And here now we're getting, with the incoming tide, we're getting a higher pH with the incoming tide. And so the pH and the tide are now lined up instead of the opposite. And so we're seeing in this case that once we get that shift, that relaxation, now instead of bringing in this lower pH water that the tide was doing, now we get this relaxation, and we're getting that the tide and the pH are actually bringing in higher pH water. So again, even though we don't have that shift where we had the tide bringing in the higher pH water, we see that the tide is still controlling the pH in the bay. So that is our motivation. Oh, and then of course, we see a pattern here with the chlorophyll. So now we can look at the biological pattern as well. And we see that if we look again, A is going to be in Humboldt Bay, and B is the comparison at Trinidad. And so we see here again with the chlorophyll that we also have that same pattern, that same tidal control on both the pH and the chlorophyll. However, if we look at Trinidad, we don't have that same tidal pattern in the pH and the chlorophyll, but we do see that as the pH drops, when we have that upwelling event, then we'll see that rise in the chlorophyll. And so we can see that is what's going on here in Trinidad, whereas in Humboldt Bay, it's being controlled by the tides. All right, very cool graphs. Now, that was the controls on pH. And so what we saw is that the pH was mostly controlled by a tidal influx from coastal waters. And it was also, I didn't show this as much right there, but it is being controlled by that carbonate sediment dissolution. And we do also see effects by biological productivity and respiration. All right, so that big control of the tidal influx from coastal waters is why we're focusing on the tidal controls of the currents in the bay. So the two stations that we're using right here, these are NOAA port stations. Ports is the Physical Oceanographic Real-Time System. And we have two stations, one at Chevron Pier and one at Hookton Channel Marker 3. And if we look at these stations, this is one that at Hookton Channel Marker 3. This is Emma Modrick and Karina Birnbeck up on top of Channel Marker 3. And this is what the instrument looks like when it's out of the water. So this is our ADCP out of the water when we're working on it and maintenance that we have out here at Marker 3. And we have one as well. Here's a picture from Chevron. And so this instrument is our ADCP. So that's the Acoustic Doppler Current Profiler. And it's sending out this acoustic signal, getting a ping off what's going on in the water column, getting it back, and we're getting a Doppler shift and seeing what that current is. And we get both the long channel and a cross channel currents. So looking at those currents, we wanted to see what we could figure out about the currents in Humboldt Bay. So here, first of all, is just a plot of that data. So the data from NOAA. This is at Chevron Pier, and this is at Hookton Channel Marker 3. And so you can see that the data is following along very clearly with the predicted tide. So again, we have a very strongly tidally controlled bay. And so we expect to see that we get those data points going right along with the tide, which is what we usually see. So taking some of this data, we wanted to look at the velocity from our instruments. And if we look at this data right here, this is from Marker 3, so out in the middle of the bay. Well, it's close to the entrance channel. We're looking at, these are the along channel currents. And when we look, we see that they have a definite up and down signal where sometimes it's going one way, sometimes it's going the other. And if we blow that up a little bit, we can see very clearly that right here we've got each day we're getting a very strong tidal signal. And that's what we expect to see. We expect to see our mixed semi-diurnal tide with 2 uneven highs and 2 uneven lows throughout the day. And so that's the signal that we're seeing in our data just by looking at the velocity data. But we wanted to get more than that. We didn't just want to say, okay, well, we see a mixed semi-diurnal tide. We see that we got a spring, we got a neap. That's great. We expect to see that. But we wanted to see a little more about what can we get in the details of what kind of components there are of the tide. And so to do that, what we've done is a Fourier transform of this velocity data. And so when we do that, what we're able to do is now looking not just at that velocity and how the velocity is changing, we're now looking at the energy spectral density plotted versus frequency. So if we look at the frequency, we can then say, well, what are these different peaks, these energy peaks? And the energy peaks we see are indeed at the M2 tidal harmonic. So it's right there at that semi-diurnal frequency. We expect that. And then we also see the diurnal. We see 2 of our diurnal peaks. We see K1 tidal harmonic right here. And then we also see the O1 tidal harmonic. And that one's also giving us our, we're getting some of the diurnal signal there. And then we see some other interesting peaks. So we got some semi-diurnal, we got some diurnal, we expect that. And we see some other peaks. And some of these peaks are at 8 hours. And some of these peaks are at 6 hours. And these are over tides. So we got some data, so we can see that we do have some energy coming in from these over tides, right around 6 and 8 hours. And so we're getting some energy there as well. This is from Marker 3. And here we also looked at the north-south currents in Marker 3. And similarly, we see the same peaks. got cut off a little bit. But we do see the same peaks. However, there's a different amount of energy in our north-south currents versus our east-west currents. And we also wanted to see if we could compare that to what was going on at Chevron. So here are two different time series from Chevron. And these two time series we've plotted together. And if we plot these together, we have the first time series was from February to April, and these were continuous time series. And the second time series here in blue is from April to June. And when we do the Fourier transforms here, we do see again our main peak here at the M2, that's the semidiurnal tidal frequency. And we also see, I've also indicated here, K1 and O1. And we do see these other peaks, these overtides that we were seeing in the other data. However, the level of energy isn't exactly the same here at Chevron as it was at marker 3. But taking these values, we wanted to see if we could calculate then what that distribution is between the semidiurnal and the diurnal. And so we calculated the form factor. And so when we look at the form factor, we're taking the energy at each period, and we're getting the this is the M2 tide here, and we're getting the approximate energy for each of those, and we're able to use that to calculate our form factor. And so we use that, and we are able to see how the energy distributes between the diurnal and the semidiurnal, and we're also able to then calculate what that distribution is at Chevron versus at marker 3. All right, this is a work in progress. We're still working on getting all the data. My students are still working on it, and I want to give some shout outs to them. Here's Taylor Jukow working out at Chevron. This is Izzy Marcus and Emma Modric on the way out to the marker. Noe Camarillo working out at maintaining that ADCP out at Chevron. Here's Caitlin Williams out on the boat, and here's Karina Birnbeck with me out at marker 3. All right, thank you.